Hello everyone, welcome back. Let's talk about another medium problem on Leetcode today. Maximum chunks to make sorted. Leetcode 769. In this problem, we are given an integer array of length n that corresponds a permutation of the integers in the range 0 to n minus 1. So for example, if array length is 5, then the integers in the array are in the range 0 to 4. Then we want to split the array into some number of chunks or partitions and individually sort each chunk, and after concatenating them, the result should be equal to the sorted array. And we have to return the largest number or maximum number of chunks we can make to sort the array. Also in this problem, constraints are really important. We are given that n is equal to array.length and n is more than equal to 1 but less than equal to 10. And each element in the array is in the range 0 to n and all the elements in the array are unique. So we are dealing with very small arrays here. Now coming to example 1, for the given array, maximum number of chunks we can make to sort the array will be 1. That is, we don't make a partition at all. And then the sorted array becomes 0, 1, 2, 3, 4. So our answer or maximum number of chunks will be equal to 1. But if we try to split this array into chunks, say for example between 3 and 2, then this chunk will be sorted. We will get 3, 4 and this chunk will be sorted. And now when we concatenate these two chunks, we will get output as 3, 4, 0, 1 and 2, which is not sorted. And no matter how we partition this array and sort and concatenate the chunks, we will never get a sorted array back. Then in example 2, we can partition the array between 1 and 0. So we will get two chunks 0, 1 as one sorted array and then 2, 3, 4 which is already sorted. So number of chunks here are equal to 2. But we want to maximize the chunks, right? So we can also partition this chunk further and get the chunks 2, 3 and 4. So our total number of chunks will be 1, 2, 3 and 4. And that's why our answer will be equal to 4. Now in terms of solution, one of the naive approach can be to put the partition at every possible index in the array so that we create multiple chunks and then sort and concatenate the chunks and see if it matches the expected sorted array. For example, we can put the partition between 1 and 0, sort and concatenate respective chunks and see if it results in a sorted array. If it doesn't, then we backtrack and try to put the partition between 0 and 2. If this works, then we try to put the partition between 2 and 3 and so on. But the time complexity of this approach will be O of 2 to the power of n into n log n, where n is number of elements in the array. Because at each point we have a decision to make that whether to add the partition or not, resulting in the time complexity of O of 2 to the power of n. And then for each operation, we have to sort the chunks. So this will result in time complexity of n log n. And then we combine the chunks and check if it matches the expected sorted array. And that will take time complexity of O of n. So overall, because of this, the time complexity is O of 2 to the power of n into n log n. And given the constraints of this problem, this may actually work because n is less than equal to 10. But we can definitely do better than this. If we look at the constraints of this problem a bit closely, we are given that all the elements in the array are in the range 0 to n minus 1 and all of them are unique. So the final state after sorting the array will be that each element in the array represents its own unique position. That is, for any value in the array, the corresponding index is where the element must end up in the end. For example, 0 ends up at 0th index, 1 at first index and so on. For example, for this array, the sorted array will be 0, 1, 2, 3 and 4. So we can see that there is a mismatch at the position of 1. But whenever the elements are at the same index, we can actually form their own chunks because we want to maximize the number of chunks. But whenever there is a mismatch, we have to chunk the elements together. For example, we chunked 1 and 0. And why we have to do that? For that, notice carefully that sum of 0 and 1 in the final output matches the sum of the chunk 1 and 0. So if the sum matches properly, this means this is a valid chunk because it is at the correct position relative to the final sorted array. So how about we form a prefix sum from the original array and the ideal sorted array and compare the prefix sum at all the indices. And whenever the prefix sum matches for the original array and the ideal array, that means the elements within that indices form a valid chunk and we will increment the chunk count by 1 and we will continue to do so until the end of the array. For example, the prefix sum for the input array will be 1, 1, 3, 6, 10, and prefix sum for ideal or sorted array will be 0, 1, 3, 6, 10. Let's also initialize chunk count to 0. Now we will traverse both array sum and ideal sum. At 0th index, we see array sum is not equal to ideal sum. So chunk count stays 0. Then at index 1, array prefix sum is 1 and ideal prefix sum is also 1. So that means this forms a valid chunk. So we increment the chunk count by 1. Then at index 2, array prefix sum and ideal prefix sum are both 3. So that means we again found a valid chunk. So we increment the count by 1. Now chunk count becomes 2. Similarly at index 3, array prefix sum and ideal prefix sum is 6. So chunk count increases to 3. And finally at last index, array and ideal prefix sum match and are equal to 10. So we increment the count to 4. And now we are done with all the elements. So we will return chunk count as 4. So the time complexity of this approach is O of n, because first we are going through the input array to compute the array sum, and then we compute the ideal sum, which also takes O of n time. We don't have to sort the array for that. We can apply prefix sum on indices for that, because in ideal sorted array, element value is equal to index. And then again we go through the array sum and ideal sum and compare the prefix sums, which will result in time complexity of O of n. So overall, the time complexity stays O of n. And in terms of space complexity, it will be O of n for storing the prefix sum for the original array and ideal sorted array. Now this is a decent time complexity, but can we also save on the space? For that, let's look at the chunks again. In the ideal sorted array, elements will end up in the position where index is equal to element value itself. And now we have to form the chunks in such a way that sorting the chunks and concatenating them results in the sorted array. So think of chunk like a water aquarium and numbers as fishes, where fishes can easily move within aquarium, but they cannot jump to other aquariums or other chunk. Because we can sort the individual chunks, allowing each fish or the numbers to swim through that aquarium and reach the correct position, but they cannot jump into another chunk. For example, in the given array, we can see that one such chunk is 1, 0. Numbers will come at the right position. That is, number 1 will come at index 1 and 0 at index 0. Similarly, if the array was 2, 0, 1, 3, 4, we can't have a partition here, because for 2, the right position is at this point and the fish or the number cannot cross the partition. So the right partition for this array should be at this point, so that 2 can easily navigate to second position. And if it can do that, then the smaller elements 0 and 1 can move to their right positions as well. So the main idea here should be to track the largest element or the max element in the subarray and see if it can reach its corresponding index. And if the maximum element can reach its index, that means that particular subarray will form a chunk, because all the smaller elements can automatically then reach their own indices. And because we have found a chunk, we will increase the number of chunks by 1. Now let's see this in action. So initially max can be set to 0. Now first element we see is 1 and 1 is more than 0. So this is our new max and index value is still 0. So we cannot form a chunk yet. Then the next value we see is 0 and max stays 1. But the index is now equal to 1. So now that means 1 can flow to this point and this will result in one chunk. So we increment our chunk count to 1. Then the next element we see is 2. So now our max becomes 2 and the index is also 2. So that means 2 can also flow to its point, but 2 is already here. So that means now the count becomes 2. Similarly, for the next element, max becomes 3 and index is also 3. So count becomes 3. And finally, for the last element, again max becomes 4 and index is also 4. So the count becomes 4 and that will be our answer. So now the time complexity is still O of n, but the space complexity reduces to O of 1, because we are just using two variables, max and count. So now let's jump into the code part. First, let's create a counter count to track how many valid chunks we can create. Let's also initialize maximum to keep track of the maximum value we have encountered so far. Now we will iterate through the input array, and for each element at index I, we will update the maximum value. And if maximum value is equal to current index, that means we have found a valid chunk, and hence we will increment the count by 1. And finally, once we are done with all the elements, we will return count as our answer. Now let's submit this code. Awesome. So that's all for this video. I hope this video was useful to you. If it was, please give it a thumbs up and share it with others who might benefit from it. If you haven't subscribed the channel yet, make sure to hit the subscribe button and turn on the notification bell so that you never miss an update. Your support helps me create more content like this. If you have any questions or suggestions, feel free to leave them in the comments below. Thanks for watching and see you in the next one.